Today we're going to go into a topic that will probably occupy us for tomorrow or for Thursday as well. It is a topic which articulates with some of the discussion we've had about the Liskov substitution principle, in the sense that it's about type hierarchies, it's about object-oriented programming and vulnerabilities of it. But it's different from that topic. It brings up a whole new type of vulnerability that exists in the subclassing context that goes beyond merely the concerns that we had brought to the fore about safe subtyping. Okay, and this is probably going to take more than this class, not least because of the late start. And I'm going to be trying to walk through it in a way that's a little bit slower than I have in some previous years where I tried to wedge it into one class. So I want to start by reflecting on the fact, reflecting on what happens when we declare a subclass in something like Java, or for that matter, something like Scala, or something like C++, or what have you. So there's two things, and we focused it to this point on the first of them. So firstly, the compiler takes a look at this subclass, and it recognizes that the type, the contract associated with the subclass, is a subtype of that for the superclass, and that allows us to pass around instances of the subclass as if it's an instance of the superclass, right? So on this very board, we had an illustration. So if we have A that's a subtype of B that's a subtype of A, or B that's specifically a subclass of A, we can pass around to B as if it's an A, right? We can have a method that takes A's and we pass it something that's secretly a B. And all it knows is that it's an A, right? We spent a bunch of time talking about that and talking about the implications for what B needs to guarantee, how consistent it needs to be with A to avoid someone being really surprised by getting a B instead of an A. To avoid us breaking their code, which is counting on the features of A when we give it a B. But there's a second component of what happens when you declare a subclass, which is the implementation of the subclass automatically inherits, and that's the term that's often used, the implementation details, specifics of how the superclass is implemented, okay? So subclassing is more than subtyping. Subtyping is a relationship between promises, and we need to maintain promises for B that are consistent with those of A. Contract with B that's consistent with the contract of A. But here we're dealing with something more with subclassing. We're dealing with inheritance, we're dealing with reuse of implementation, okay? So the implementation mechanisms of the superclass are going to be available to the subclass. And particularly early on within object-oriented programming, this was seen as something at least as important as polymorphism, as being able to pass around to B as if it's an A. It's this ability to reuse the implementation of A. And the thought was that that would avoid needing to write a lot of new code. We could just sort of tag on new things to the implementations. But it also led to a lot of problematic frameworks for subclassing in the early years, until Barbara Liskov and Jeanette Wing clarified what it really means from a Liskov substitution principle to be safe. But it turns out there's more than that. There's issues having to do with subclassing that are distinctive beyond those for subtyping. So I want to make sure, first of all, that we are rock solid in terms of a basic feature of subclassing, okay? So suppose here we have a class A, it's a superclass, and a class B that extends A, okay? And suppose A, the superclass, defines foo and bar. So it defines two methods, foo and bar. And suppose further that foo calls off to bar. So foo calls bar. Great. Now, if we allocated an instance of an A, and we were to call foo, it would call bar. Right? It would call its own bar, right? If I said I have an A, and I created a new A, and then I said A dot foo, as part of executing foo, it's going to call off to the bar in A, right? Bar in class A. Okay, very straightforward idea. Now, we can have B extending A. So B is a subclass of A, right? Now here, B overrides bar. It doesn't override foo, it overrides bar, okay? So B is extending A by creating a new implementation of bar, okay? It overrides it. So B has foo, inherits that from A, right? But it also has its own bar, right? Yeah. Okay, now, suppose now we have a client of these. Someone is going to use them, sort of customers of them. Someone is going to make use of them. Okay, so we have a client class. And suppose that in the client class, we have something called here Baz. This is a method, okay? And Baz allocates a new B. So it allocates one of these guys, one of these class Bs. And then it calls foo. I want to ask you so it's calling foo on a B. Which foo is going to be called here? As a sanity check. Which foo is called?
The inherited one.
Yeah, it's the inherited one. It's the one B inherits from A. Which bar is going to be called by that foo? Sorry? The overridden one. Right? The bar in B. So we're calling off here to foo, and that's going to be the foo inherited by B. That foo calls bar. But because bar has been overridden in B, and because this is secretly a B, well, it's not so secretly here, right? Because it's clearly a B. Well, it's not because of it, but it is clearly a B. When we call foo, it's going to call off to our bar here, right? This is a B. Are we comfortable with that? Are we on the same page with that? Okay. Now, the plot thickens slightly. Suppose that client class further has a method called zap, okay? Which takes something that's ostensibly an A. It appears to be an A. Its apparent type is A, right? And it calls foo on that thing, apparent type A. So we're calling, after allocating B and calling foo on it, we're going to call zap with B. So we're going to pass this thing that's secretly a B, pass thing whose actual type is a B, to zap. And we're going to pass it this thing that's a B. But it masquerades as, it appears to be an A. We call foo on that object, this thing called A. Whose foo is going to be called? Sanity check. Whose foo is going to be called here?
There's only one foo.
There's only one foo. It's on an A that's been inherited by B. Okay, great. Whose bar is going to be called? The bar in B. The bar in B. Because the apparent type of this A, lowercase a, is A, the apparent type, but secretly it's a B. Right? All B's have an overridden version of bar. They have an inherited version of foo, which they're using. But that foo, because they've overridden bar, when it's called, it's going to call their bar. Are we clear on that issue? So regardless, and this is the thing I want to emphasize here, I want to make sure we're all on the same page with this, regardless of whether we are calling foo on something whose apparent type is B, or merely something whose parent type is A, but its actual type is B. When we call foo, it is in fact calling, that foo is in fact calling the bar that's in B. Are we all okay with that? Okay. Okay. Good. Because we're going to be relying on that fact quite a bit for subsequent understanding. Again, if anyone is not sure about this, come talk with me. But this is very, very important part of what it means to inherit and override something. We're inheriting A. B is automatically getting the foo in A. It inherits that because it is a subclass of A, not merely subtype. But because it overrides bar, anything that it inherits that calls bar is calling its own bar. Okay. Okay. So let's go on here. So the answer here is, it's calling in both cases here. It is calling this bar. That's a very foundational sort of type of understanding. Okay. Okay, so ladies and gentlemen, we've spent a while talking about the Liskov substitution principle, and I want to come back to this example that I sort of snuck in at one point here. So ladies and gentlemen, here we have a contract for a supertype called hash set and for a subtype called instrumented hash set. And here's the contract for hash set. It has add all as two methods in it, okay? And you can see the preconditions, postconditions. And then instrumented hash set, it's going to have a contract where it maintains those basic features of add and add all, but it's going to maintain some additional information. So when we do an add in the subtype, instrumented hash set, it's going to, just like in the supertype, it's going to add in the thing to the set, but it's also going to keep track by incrementing an insertion count. So if asked later, it can tell us how many things have been inserted. And similarly, add all here, given a collection C, it'll add each of the elements of that collection to its internal set, but it'll increment the insertion count for every one that it adds, okay? And if we ask it in a new method, get add count, if we ask it, hey, get me your add count, it'll return for us the insertion count that we've accrued thus far, the number of times we've inserted something. Does that make sense? So instrumented hash set is just like any old hash set, except it's keeping track of some extra information. It's not interfering with the normal operations of hash set, but it's keeping track of this insertion count and gives it to us if we ask for it. So let me ask this. I want to be clear about this. Is instrumented hash set a legitimate, that is a behavioral subtype, as judged by the Liskov substitution principle for hash sets? Is it? Yeah, it is. Completely legitimate. There's absolutely no problem with this. If we remember the scenario you go through when reasoning this through. If we thought we had a hash set, if we had something whose apparent type is a hash set, but it secretly was an instrumented hash set, could we be rudely surprised because it does something totally unexpected? No, we wouldn't know that it's accumulating this extra insertion count. And accumulating that extra insertion count in no way interferes with the operations, the semantics we're counting on, but kind of the meaning of how it's supposed to work from the perspective of hash set. Is that right? In no way interferes with it. Somewhere else in the program, it could be calling, hey, get me the add count, and that doesn't screw anything up either. And somewhere else in the program, it's calling get add count or whatever. Somewhere else in the program knows it's an instrument hash set. It can't do us any harm in terms of its behavior. So instrumented hash set is a perfectly legitimate subtype of hash set, okay? From a Liskov substitution principle. There's nothing to be faulted about it. Perfectly reasonable. Doesn't break the Liskov substitution principle at all. Anyone have any concerns about that? Because this is going to be important to understand. Okay. Instrumented hash set, if I put that on the final exam, It's a perfectly legitimate subtype of hash set. Great. Okay, but now we get into the domain, ladies and gentlemen, with subclassing. What we're talking about has to do not just with promises, these sort of promises, but critically with implementation. Because, ladies and gentlemen, this issue of inheritance, reusing mechanism, is a matter of implementation. It goes beyond just the promises made, but to actually how things are implemented. So, I would argue that while instrumented hash set is a perfectly legitimate subtype of hash set, as a subclass, there may be risks associated with it. Even though, from the promises standpoint, from the contracts, it's perfectly legitimate, there are implementation risks. And I would say that here is one implementation. I'd like you to comment on the risk associated with this. We saw this earlier, some of you might remember it, and that's fine. I'm trying to separate this issue of subtyping from the extra issues that come in with subclassing. So here we have a declaration of instrumented hash set, and here we have add and add all declared as methods, and here's get, add, count. And you'll notice that per their promises, add, it always simply calls off to the add of the superclass, the hash set, and add all similarly. It calls off to the add all of the hash set. But beyond that, per its promises of the subtype, the instrumented hash set, it increments this add count, this count of the number of times that something has been added. And if we call get add count, it will return that. So I would argue that while this type, instrumented hash set, is a perfectly legitimate subtype of hash set in terms of its contracts, the promises it makes, I would argue that this implementation is risky. And I'd like you to tell me why. Yes?
It increments before testing the validity of the add, for one thing.
Okay, it is incrementing prior to that, but here we can assume that add count I don't provide it in with additional detail, but we'll assume that add count is just accumulating the number of times something has been requested to be added in. So
saying if it doesn't actually get added because of an error, you still accumulated it.
Okay, if there's an error, yes, this is true, but that's actually not the concern. So that's an interesting point. If there is an error, for example, if O were null, and that were flagged in the superclass, then we already would have said it's added. It's true, but that's not actually the issue that I'm after now. What's the other bigger vulnerability?
It relies on the implementation of add all.
Okay, it relies on the implementation of add all. And whose implementation of add all?
Superclasses.
The superclasses. So give me a reason that this code might not work from that perspective. Yes?
Because add all might not be implementing the count the way you expect it to, because the subtype is the one that's incrementing it using add, right? Add count.
Okay, yeah, so the subtype here is incrementing the add count, yeah.
But the super's add all might not be calling the subtypes add, so you're not going to
Okay.
increment them.
So you've hit on the basic issue, but let's refine that a little bit. So suppose the supertypes, the superclasses, we'll be more specific, the superclass hash set's implementation of add all does not call add. So all it does is internally it adds, for each element of the collection passed to it, it adds that into its internal set. Would this be problematic then?
Nope.
No, it works fine in that case, because here we've already recorded, we've added in this many elements from this collection. suppose add all, by contrast, in the superclass does call add. Whose add is it going to call?
Ours.
Yeah, the subclasses, instrumented hash sets add. Could there be a problem with that? Now it's double counting, right? We've added it in here in add all in the subclass, but then we've gone off and delegated to the superclasses add all, and if that calls add, whose add it's going to call? It's going to call the add in the subclass, where again, for every time we add it in, it's going to add in plus, right? So here we're double counting it, are we not? We're double counting, ladies and gentlemen. Okay. So here we have a vulnerability, and the point is that we don't know, will this be correct or not, right? Because it may depend on code to which we don't have access in the hash set over here on the left. I don't know why there's something broken. This should say hash set here. Okay, so there we go. So the problem is we don't know for the superclass which of these is correct without testing it. Suppose we did have access to the superclass implementation and we saw that add all does not call add. It just adds it indirectly. Would we be safe?
No,
Not forever.
Oh, superclass might evolve, right? Even if it works now, even if we test this and it works, there's no guarantee. If we don't control the superclass, maybe it will work now and it won't work 6 months from now. It'll break our code. Do you see that? You see that? Why that is? Here, the correctness of our subclass implementation is now entangled with, dependent upon the implementation of hash set. The promise, this is not an issue of promises, the contracts. The contract of the subclass, that type associated with it, is still saying we're only supposed to add 1 to the count, and it's promising to do all the things the superclass is. What's going on here is an issue of implementations. Does the implementation of the subclass, is it correct given the implementation of the superclass? And if the implementation of the superclass changes, like later add all does end up just calling add, then suddenly our subclass no longer works. Do you see why that could be an issue here? Okay, now this is one type, but it's not restricted, one case where this comes in, but it's a more general phenomenon. So let me ask this. Here's another case, right? So we have a simple superclass and a proposed subclass of it. So from the standpoint, so the superclass, it keeps track of, as part of its operations, it keeps track of an int, its current value. You could think of this, as being a sort of counter or what have you. You can call get value on it, set value. Get value will get the current int value, set value will set it, and we can ask, is it positive? Okay, and it will return if it's greater than 0, true, otherwise false. Okay, is positive. And I propose to create a subclass of this that overrides set value and get value to sort of keep track of it myself in the subclass. And the question is, does this subclass adhere to the Liskov substitution principle? If I passed around, in terms of the promises made, in terms of the promises made by the subclass, is there any problem with this from a standpoint of the Liskov substitution principle?
There is no implementation of the is-positive class or is-positive method there. So that method is going to call the value of the simple
Okay, so we're gonna get to that. That's an issue of implementation, but from the standpoint of the promises made, remember, Liskov substitution principle is about promises. It's about the contracts in terms of what's guaranteed precondition-wise, post-condition-wise, and variance history properties. Is there a problem with the subtype from the standpoint of the Liskov substitution principle? No, there's no problem. There's no problem with it from the standpoint of the promises made. Is there a problem with respect to the implementation? So from the standpoint of promises, if all I had was a subtype that adhered to these promises, and I passed it around as if it were an instance of supertype to something that was expecting an instance of supertype, I gave it an instance of subtype. In terms of promises made, there shouldn't be a problem. But what has been noted here is that there's a risk associated with implementation. What's the risk associated with implementation? Yes, Connor.
Is it that you made a new value, and if they're using the other old one as a public, then it wouldn't be getting updated?
Okay, it's not so much as a public, but you're in the right area. You're in definitely the right area. So what's the risk here? And he mentioned it earlier, and it's something to do with is positive. Could you imagine a case where, given the subclass, is positive still works? Give a case involving the implementation of the superclass where is positive will still work in the subclass. If is positive does what? Calls get value. Because if is positive calls get value, that is positive implementation is inherited by the subclass. And when we call is positive on an instance of the subclass, whose get value is it going to call? Subclasses, the overridden one. Here. It's completely isomorphic to this case earlier, where we have an instance of superclass, the instance in a subclass. The superclass defines here is positive. You could think of as foo. Get value is bar. The subclass overrides get value, just like this overrides bar. And then the superclass here is positive. When we call the superclasses is positive, whose bar is it going to call? Yeah, not Ghostbusters. Yeah, it's going to call that in the subclass, right? So here, ladies and gentlemen, if is positive calls get value, the inherited version of is positive in the subclass, when we call is positive, it will call get value here, and things will work hunky-dory. Do they still say that in your generation? Okay. Maybe I'll reintroduce the trend. It's really nifty, I'll tell you that. Okay, so ladies and gentlemen, actually, when I was growing up, hunky-dory was past, but that's okay, I like that. Okay, so it's copacetic. So, ladies and gentlemen, suppose is positive, by contrast, does not. Suppose its implementation in the superclass does not, in fact, call get value. Suppose it just internally checks the value without calling get value. Would the subclass work?
Sometimes.
No.
No, it would sometimes. Because if you kept setting it to things greater than 0, positive would still be okay.
Well, okay. So particular instances, it might sometimes work, just like a clock that's frozen is correct twice a day. But in general, it would not be viable. It would not work. Is positive would not work under the broad set of possibilities for how it can be used. So, ladies and gentlemen, here, this is not a matter of Liskov substitution principle. This is a matter of implementation, and whether this implementation of the subclass is going to break the implementation of the superclass. Is positive going to be, when it's inherited, is it going to work? depends on how it's implemented in the superclass, whether or not we've broken it when we declare the subclass, and whether it will continue to work depends on whether it will continue to call getValue or whether that will change. And so once again, we have this entangling of implementation correctness where the subclass to be correct depends on how the superclass is implemented and how it will evolve over time. Okay? This is not a Liskov substitution principle issue with the promises made. It's an issue of whether those promises are in fact guaranteed by how it's implemented. Okay, so the answer is this safe? No. Okay, so challenge here is that with subclassing, we have two sets of issues coming in. One is the whole Liskov substitution interval. We have to make promises for the subtype that are consistent with those of the supertype. So we don't rudely surprise someone who thinks they have an instance of supertype, but we actually give them an instance of subtype. But secondly, we have to be very careful about how we subclass, our implementation of the subclass. Or else that implementation may deviate from our promises. It won't actually, in fact, guarantee the behavior we're talking about, okay? So we might break the behavior of the superclass methods that we inherit, like break the behavior of isPositive. Or we might depend on things, implementation details of the superclass that change out from under us. About, for example, does add all call add? And we're counting on one thing, and and it ends up being broken by the behavior, by the evolution of the superclass. So we have concerns about promises, which are the province of Liskov substitution principle, and concerns about implementation. And we're going to be talking about ways to guarantee safe subclassing in terms of implementation. Okay, this has to do with how it's implemented, how it's realized, how those promises are realized. And the challenge is how to guarantee it when we can't even see a lot of the implementation in the superclasses because it's not available to us or it might change over time. So here, we're dealing with a situation where if we have a subclass, generally it's overriding some methods of the superclass, and it's using some methods directly as inherited by the superclass. And generally we can't see the code to those methods. And even if we can't see it now, it might change, right? It could change at any point because it's not under our control. It's under the control of the people who wrote the superclass. And the realization here is generally we need to rely on some details of the implementation, how they work when we're creating this subclass. And as a result of that, counting on those behaviors, the implementation of the subclass is tied up with that of a superclass. So what we're going to be going towards as one strategy is a subclassing contract for the subclasses to basically say what's guaranteed for subclasses. Now I want to reflect on this by going up a level here and make sure that we are on the same page. So from the standpoint of Liskov substitution principle, the promise is made. Do we care about whether add all calls add? From the standpoint of the promises made in the Liskov substitution principle, do we care whether add all calls add internally or not? No. All we care about is that it adheres to its promise specification. We don't care whether add all calls add. From the standpoint of the Liskov substitution principle, do we care about whether isPositive calls getValue or not? No. From the Liskov substitution principle, as long as it does its job, as long as it adheres to that promise, we're fine. We're in fine shape. But from the standpoint of implementation of a subclass, we sure as heck care. If we're going to have a subclass that isn't broken in 6 months' time, when they change how the superclass is broken, we sure heck is positive is going to call get value or not, and whether that's guaranteed from now on. We sure as heck are going to care whether add all calls add now and whether that's guaranteed going forward. Do you get that distinction? So it's a separate issue from Liskov substitution principle. Liskov substitution principle is about promises. This is about implementation. Okay. So absent some sort of guarantee here, there's some real risk. The subclass can be broken by changes in the superclass. So add all used to call add. We've come to rely on that. We relied on it, say, in putting in place this mechanism here. So we in fact, if add all calls add, we in fact don't want to have this increment here because it'll be incremented every time we call add. And if that suddenly changes, then it's going to break our implementation. Okay? So the subclass can be broken by changes in superclass. But the superclass functionality, how the superclass methods work, like is positive work, can be broken by changes in the subclass. We can have a change in the subclass which breaks that functionality. So if we override a method in the superclass, within that subclass, if we do an override there, it may break the consistency between methods in the superclass and subclass. Okay. So, for example, here, imagine if we in this case ended up overriding set value and get value, but we didn't override is positive. That might break the functionality of is positive. If is positive internally refers to the integer behind the scenes here in the superclass, then suddenly we'll have broken that functionality. Or imagine if we overrode set value, we didn't override get value together with it. Now, get value might not work because set value is setting a different method and get value is reading a different one altogether. So, ladies and gentlemen, without some sort of promises here as to what's guaranteed for the subclass, we might break functionality. The superclass can be broken by changes to the subclass or changing what methods are implemented, and the superclass can be broken by subclass can be broken by changes in the superclass. And this is fragile. Again, we don't want the interconnection of our digital world to mean that some change off in this office totally breaks the code in this other office. And if we're creating a subclass, it's very disconcerting to have the prospect that it can break at any time just because the superclass evolves willy-nilly in a different direction. Okay. So going back to that analogy, the FedEx and FredEx analogy, there's a bit of an analogy here with that. So to be a legitimate FedEx franchise, to set up shop as that, you need to undertake two things. One thing is you need to make promises that are consistent with promises of FedEx. So if someone brings in their package by noon, you have to promise it that it will get to its destination by 5 p.m. the next day, anywhere in Canada or what have you, for a certain rate of service. So that's one sort of thing that you need to consider. The second thing is you actually have to deliver on those promises. And here, not only do we have to make the promises, we have to actually be able to deliver them. So if we have a FedEx franchise and we plan to rely entirely on sled dogs, for example, that would be an exciting business proposition. We might get some novelty customers, but it would be hard to guarantee that the package would be in Newfoundland by 5 p.m. the next day. Even with the very finest of sled dogs, it would be a challenge. So, ladies and gentlemen, dealing with inheritance in classes where you have one class that inherits from another, it's a little bit like imagine if a FedEx franchise of FedEx, when you set up as a FedEx franchise, not only do you have to adhere to promises like that, but you have to actually adhere to their implementations, their systems. All the planes they use, the delivery trucks, the IT system, etc. And here, we are relying on implementation details of FedEx. From a customer's perspective, they don't care whether add all calls add, as long as it does its work. From a Liskov substitution principle, we don't care. But from the standpoint of implementation, we sure care. If we're going to be set up as FedEx, we're relying on the implementation details of FedEx. We need to know something about how FedEx systems work so that our system will work properly, and so if they evolve their system, it doesn't break our system. Okay? This is more than customers need to know. But if we're going to set up as a FedEx franchise in a way that reuses all their implementation, we need to know about that implementation, right? If we need to know, if we're going to use their planes, we're going to inherit access to their plane system because we're a franchise, we need to know their plane schedule, when they fly, etc. And so it is when you're subclassing another class. You need to know more than just the customer. The person who uses an instance of that class knows. So if we use an instance of A here, we need to know one level of thing. We call a.foo, we need to know what it does. But we don't know, for that case, to know whether foo calls bar internally, etc. But if we're creating a subclass of A, a subclass, not merely a subtype, we sure do need to know something about whether foo calls bar, because we want to know if we override bar, is it called by foo, for example. Okay? So there's several ways we're going to go through that we can deal with subclassing. The safest way of all, the way that's simplest, but the way that is typically off the table for many implementations of subclassing is you prevent it. You make it impossible to subclass. And there's two basic ways of doing this in Java. One is you declare a class as final. You say final class, whatever. Okay? That means that class is not subject to subclassing. If someone tries to subclass it, they'll get rejected in that regard. Method two, you make the constructors private or package private, and you use the static factory method associated with that class itself to create. So that factory method calls, because it's in the class, it calls off to the private constructor and constructs something. But in that case, you can't subclass it. You can't delegate to these constructors, to the constructor of the class, because the constructors are private or package private. Okay? We are going to see also later how we can use wrapper classes and compositions. So probably next time, maybe the time after that, as an alternative to inheritance. So in many cases, we can avoid subclassing. We can, very importantly, if we create a class, we can design it in a way that prevents it from being subclassed. Okay? But we're going to go through a set of methods that allow us to more safely subclass a class. If you wish to allow it to be subclassed, you can do so with much greater safety. Okay? So the first of the ways, not surprisingly, based on my comments, is we're going to look at a means of providing a contract aimed not at users of instances of the class, not at users like where we call a method based on a reference to an object of that class, to an instance of the class, but rather contracts aimed at people who are subclassing. Okay? And the idea is that this contract is going to provide more information that a user of an instance requires. The user of an instance doesn't care if foo calls bar. The contract for a subclass, for someone who wants to build a subclass of A, is going to say, does foo call bar? Because they want to know how it will affect things if they override bar. Okay? So there's going to be some implementation regarding how that superclass is implemented. Okay? and we'll see a little bit about how we can do this. Okay. Okay. So here's a set of approaches. Avoiding is the first. We're going to go now into the subclassing specifications. So thus far in the class, we've been talking about, in the object-oriented context, specifications aimed at users of instances of a class. So what does the person who has a reference to an instance need to know when they call off to methods? What are the preconditions? What are the postconditions? What are the invariants? And what are the history properties? Right? So we've talked about. Those specifications are aimed at people using an instance. Okay. We're going to expand that for specifications aimed at people seeking to subclass. Okay. And this is an approach undertaken for the Java libraries as a way of encouraging safe subclassing. Okay, so here we're going to deal with distinct subclassing interfaces. They reveal some implementation details, particularly what methods rely on what other methods, or share data in some cases with other methods. And here, if we give too little information in subclass interfaces, the subclass interfacers might give up on the idea of subclassing or guess at properties in a way that would be broken. If we give too much information in the subclass interfaces, it limits our ability to evolve the superclass. Okay, violates their separation concerns. I want to highlight the fact, and this is an important point, that basically the same issue, same tension applies to the traditional type of specifications. If we promise too much in our specifications, we limit our ability to evolve a class. If we promise too little, people might not use our class, or they'll use it with guesswork rather than confidence, and their code might break if we evolve it. So this is an example of a subclass specification from the Java library. This is from java.util.abstract collection. And you'll notice that what it promises expands beyond what we've been talking about. So, for example, for this remove method, it comments on its functionality. It removes a single instance of the specified elements from this collection if it is present. And it gives some more formal notation in terms of this. And note that it says what the return value is. So preconditions and postconditions are provided through here. And returns true if the collection contained in the specified element, are equivalent if the collection changed the result of the call. Okay. Here, there's some further information. You notice this is information that isn't required for a user of this, but for someone who's thinking about subclassing it. So this actually says the implementation iterates over the collection looking for the element. If it finds it, removes it from the collection using the iterator's remove method. Okay. Note that it comments also on the exceptions provided if there's an issue. So the point is, it's actually telling something about what it's calling in the context of the implementation. Here's another example. This is from java.util.abstractList. Here, remove range. The comment here is this method is called by the clear operation on this list and its sublists. Overriding this method to take advantage of the list implementation could substantially improve the performance of clear operation list and sublists. So here it's providing information to subclassers about what calls what is called by what. This is an example of a subclass-oriented interface. Okay, this is one type of information that can be provided. Who calls what? Does add all call add? Does is positive call get value or not? A second approach from this is proposed by John Guttag and Remy Stata. And here, what we're talking about is providing modular ways of replacing certain functionality together. So the idea is that if you provide get method, you have to provide a set method with it. Or you have to provide get set and is positive together. So you're providing for a set of group methods that need to be replaced together as a modular unit. So replacing one means replacing all of them. This is sometimes called a specialization interface. So you're replacing a whole set at the same time in a joint way. So there, the idea is we're providing specifications to subclassers that provide additional information beyond what we provide to users of an instance. Users of an instance, we provide preconditions, postconditions, and variance history properties. To those subclassing, we indicate who calls what and maybe what things need to be provided together. Okay? So that's the second approach to dealing with subclassing. You provide extra information to subclassers that they need to do their job safely. And they know what's guaranteed, not just now, but going forward, to avoid their code breaking. So you know, okay, is positive, is guaranteed to call get value, or add all is guaranteed to call add. Not only does it do it now, it will continue to do it, and therefore I can avoid incrementing the count in at all directly. Okay, there's the third approach, which is advocated by some authors. And it's a practical approach. Doesn't require anything too fancy. It's a simple idea, but it's less guaranteed. So here, ladies and gentlemen, we confine our overridable functionality, the things that can be overridden, to just a few protected methods, okay? And basically, you use language mechanisms or specifications to prevent overriding of other methods, okay? And the deal is that rather than calling off two things that can be overridden in the superclass, the superclass, by and large, calls off to things that can't be overridden. And as a result, you won't have it being changed by a subclass that is seeking to add new functionality. Okay. So here we minimize direct impact on functions of overriding by avoiding overriding if possible. And the realization here is that dependence on overridable methods, you might think it allows for easy extension, but it complicates reasoning. So we're going to take a look at an example of this. So here we have the sort of case that we saw earlier. So we have A, which provides foo and bar, and B, which extends it and overrides bar. Okay? Now, just as a recollection, if here we call off to foo on an instance of B, it's going to call off to foo here, and because bar has been overridden, it's going to call whose bar? Whose bar is going to be called? The subclass's bar. Good. And we're seeking to avoid that. So this is what we're going to do. Rather than having foo call off to bar, a thing that can be overridden, instead, we're going to have it call off to something called bar internal. Okay? And the internal bar cannot be overridden by the subtype, by the subclass. Maybe it's a protected element. Okay? So it cannot be overridden by B. It's of course inherited by B. And so if we call off to foo here on a B, foo will call off to bar internal. We haven't overridden, indeed we can't override bar internal. And as a result, foo will work as normal. If we want to have bar, that's fine, but it won't be called by foo. It will also call bar internal. Okay? And we can override bar if we want to, but it won't change the behavior of foo. Foo's behavior will not be changed by overriding a bar because foo doesn't call bar. It calls off to something else. It calls off to foo to bar internal. Bar, the default implementation calls off to bar internal, but we can override that, but it won't break other methods. In other words, by overriding a method, you don't have to worry that you're breaking other methods. You got the basic idea here? So by overriding method X, we don't have to worry that we're breaking methods Y and Z because they call X. Because they won't call X. They'll call something that's a protected internal thing that we can't override. So if we want to override a method, we still can, but we'll do so in a simpler way that won't break other methods. Right? We override X to change the behavior of X. We override Y to change the behavior of Y. We override Z to change the behavior of Z. But overriding X doesn't break Y and Z by default. Do you appreciate that issue? Okay. So the idea is to decouple them so that we don't have this entangling of dependencies where overriding one ends up inadvertently changing multiple. Okay. So here, we're having methods call not to other overridable things, but to internal things that can't be overridden because they are, for example, protected. Okay. So you'll recall, for example, add all here called off to, it might in the superclass call add. The superclass implementation of add all might call add, in which case it'll call our add, or it might not, in which case ours won't be called. And instead, we could have confidence in this approach that add all in the superclass will never call add. So we know if we want to override add all, we can override it here. We know that we can override add to change the behavior of add when called on our class, but we won't be changing add all's semantics, its meaning, in the superclass by overriding add. Okay? So we know the superclasses add all will never call our add here. Okay. So is this idea fairly clear to people? Yeah? Each method is not entangled with others in a way that can be overridden. Each method can be overridden in and of itself, but it's not entangled with others in the sense that overriding it doesn't break several other things. Okay? Basic idea of this. So it's a bit of hygiene to prevent this. Okay, now we're going to talk about a fourth method here. Okay, this is probably the last thing we're going to be able to do in this session. So the reflection here is that rather than using traditional inheritance, we can use delegation instead. Okay, and the analogy I gave earlier is that using inheritance is like committing to use FedEx's implementation, its systems, its IT system, its planes, etc. Okay? And the challenge here is that when we have this, when we're using someone else's systems, someone else's implementation, we typically have an entangling, an intertwining of our systems and theirs. We override some things but use others of theirs, and it leads to complicated reasoning. We need to know how these things work, how their system works, to understand how it'll interact with our own. By contrast, composition, or aggregation, or wrapper classes is a particularly simple re-implementation strategy, okay? This would be like us setting up a franchise and hanging out a shingle and saying we're a FedEx franchise. But to actually ship the packages out the back, we use Purelator Courier or some other service. We act like a customer for another service. We don't have to worry about what plane schedules are, you know, the specifics of the IT system. We're just using essentially another system as a client, as a customer. So we don't need to know anything more as a customer than a typical user of those systems would need to know. Okay, so imagine we have this add all and add case. Okay. One thing that we could do is, rather than having instrumented hash set here, where we override these methods and we risk add all, for example, calling our add or not, or changing how it does that, we have something like this. So here we have a class, implemented hash set, and it implements an interface set. Okay? And internally, we actually have a set, a reference to a set. Internally, we have a reference to a set. And we provide all the methods associated with that we have to serve as a set to be passed around like a set. And most of those methods are simply pass-throughs. For example, if we clear, we clear it. If we ask if it contains, we just ask, does it contain the appropriate items? Is it empty? Is it empty? But for those that are actually going to insert things, we need to keep track of how many things we've inserted. So we're going to add those, we're going to increment those accordingly. So here add, adds 1 to add count. Here add all, adds a whole bunch to add count. So, and then we call off to the appropriate methods and add all rather in that internal set S. So here's the question. So here we have a wrapper. It's a wrapper around, instrumented set is a wrapper around the set S that for a few methods, it actually keeps track of some extra information. It bookkeeps a little bit, right? That's all it does. And for most things, it just calls off to the appropriate methods here, right? Okay, so here's the question. If I call add all on this instrumented hash set, do I have to worry about whether add all in the set S calls add or not? Is that something I have to worry about?
No.
Why not? Because what? It's a promise, okay, so it needs to promise that it works in a certain way. Why do I, okay, so yes, all I care about is the promises. So that's exactly right. All I care about is the promises. And those promises are guaranteed whether or not it calls. But here's the question. I want to make sure you're on the same page with this. Do we have to worry that S's at all calls off to our add? No. No. We no longer have this entangling of the implementations, right? Just because we have an add method here, it doesn't change how the set works that we're referring to. We haven't imposed our add as part of that set S. We haven't sort of changed out, its add, right? It's just when we call add, when add is called an instrumented hash set, we just delegate on to add in the set S. We're not actually changing how that set S works. We're just keeping track of some added information. And similarly with add all here. So, ladies and gentlemen, here with this wrapper class, with this composition or aggregation, we're not in fact changing the behavior of this set S. Do you grok that? We're not changing this at all. We're just a client. We're just a client. We're just a user of it, just like we're here a user of A when we call foo here after instrumenting it. Just like Just like we're a user of pure related courier shipping out our back door of our FredEx, right? People come in with their package, they deliver it by 12, we say thank you very much, and we just pass it to the pure related courier pickup person in the back alley, and they take it off. And we don't have to worry about IT systems or whatever, it's their business now. They have to deliver it by that certain time. Here, it's just like that. We're just delegating off to this set S. We're just keeping track of extra information beyond it. Do we get the benefits of the fact that someone's implemented set S? Yeah, we just, like any other user of it, we can call off to it, sure. But we have some ugliness. What's the ugliness? Well, we have to write these wrapper methods that keep on delegating to it. Now, probably in the next 10 years, you know, this is going to be really trivial to do for most of these. But the point is, right now, it's a little bit ugly in terms of systematically having to call off all these methods so that we implement type set. But let me ask this. Suppose set S, the implementation that we're using, maybe it's a hash set, for example. If that evolves over the next 5 years, so that initially add all did call add, and then it got optimized and add all no longer calls add, it just does the work internally, does that affect our correctness of our code? No, it doesn't. Change it at all. All we're depending on is the promises of how add and add all work. It's not entangled with our code. If the implementation of the set S works, as long as it adheres to the promises, our code works fine. Do you get that point? So, ladies and gentlemen, we're just like a user of this set S. If they want to optimize the internal mechanisms of how that works, great. We'll use all that. We'll benefit all from that. It'll be like pure related courier in the back alley becomes more and more efficient. Great. Nothing but good things. We don't have to worry it complicates our life. By contrast, ladies and gentlemen, if we had a re-implementation here, if we inherit from this, and the superclass evolves in a way that add all no longer calls add, that's a significant thing because it's entangled with our add. Because its add all is using our add, right? But here, that add all from S is not using our add. Add all, whether it calls add internally or not, we don't care, just like we don't care here when we call foo as an instance, whether it calls bar. That's up to it. As long as it adheres to its promises, it's fine. Do you get this point? So wrapping is something which can be readily done that decouples the implementations. It means each can evolve independently of another. If we later delete add from our class, or we add it in later, it doesn't affect how S works. Okay, fine. They're decoupled. They're separated out. They're not entangled. They're not entwined. And that means a load off our worry, load off our mind, because they can evolve independently. Grok or not? Grok. Okay, good. Okay, so turns out that we can undertake this in a particularly elegant way, and we're going to see next time how we can use a technique known as skeletal implementations, which is widely used in Java, incidentally, to implement some similar functionality in an elegant way. And we're going to go on and probably talk about mix-ins next time, and the use of mix-ins as an alternative to relying on subclassing for reuse of implementation. Okay? So thank you very much. Be sure to take a look at Thursday's take-home exercise. As I recall, that is one of them that's depended on by the assignment. Okay. Thanks very much.